didn't know anything about topological instrument.
But they do have no anomaly.
Yeah, this still has no anomaly, but you still have to have a, I mean, standard model is known to have no anomaly, but you still have to have a construction.
I mean, they conjectured that 16 things could be gapped out in your sector. They just didn't show that.
They didn't show it could work. They conjectured it might. Right? They conjectured it might have the middle sector gapped out. But their middle sector actually is not the boundary, it's actually not a momentum. Actually not a middle sector. And they didn't make any connection to our modern understanding of surrounding intelligent topological instrument. But one say that this goal has been tried in high energy. Okay, at precisely press scale mechanism. We have tried this. But I'm showing that we have plenty of examples to show this actually can work. Plenty of topological instrument or superconductor under interaction, we know this kind of situation can work.
I mean, do you actually have a funny thing to do this? Or
Yeah, I do. But it's going to be very hard to simulate. But I do have.
I think in the earlier paper, when they say they have no anomaly, they really mean there's no perpetuating anomaly. Or some non-global anomaly. But actually, the concern here is that in order for that to gap that model, you should have any other anomaly, and to show there's no even unknown anomaly is a little bit challenging. But mostly people in standard model say there's no perpetuating anomaly, but the model with no perpetuating anomaly can still have other anomalies. So yeah, I think this construction really shows this particular model really don't have any other.
Yeah, anyway, but the similar question can be asked in all dimensions. Basically just in 1 plus 1D, 0 plus 1D, 3 plus 1D, or 2 plus 1D, Dirac fermion or chiral fermion or Majorana fermion is originally massless, but can I gap it out using interaction? But any fermion bilinear operator equation value will be 0. Is it possible at all in all those dimensions? Okay, because of our understanding of strongly intelligent topological superconductor, we know this is possible. But actually, to really do the calculations may be subtle. So let me show you the simplest example of this, which is the 0 plus 1 dimensional example. Okay, the 0 plus 1 dimensional example is the boundary of a 1-dimensional SPT. Okay, but let me just talk about the boundary right now, 0-dimensional boundary right now. So let's consider n copies of the 0-dimensional Majorana fermions with time inversal symmetry. And under time inversal transformation, this Majorana fermion will go to itself. But time inversal is not trivial. It's always change sign of I, change sign of complex conjugation. Okay. So it means that any fermion. So if I define time inversal this way, then in this 0-dimensional system, any fermion bilinear operator, which is Hermitian, any Hermitian fermion bilinear operator will look like this: I, gamma A, gamma B. A, B are different. But this operator is going to be odd on the time inversal. Okay, on the time inversal, I change sign, gamma A, gamma A, they don't change sign, so this is odd on the time inversal. Okay? So it means that if I have like n equal to 2, I have 2 copies of Majorana fermion. The only Hamiltonian I can write down is this, but you break time inversal. Okay, so it means that with 2 Majorana fermion, I cannot have any term in the system. But then now with a 4-component Hamiltonian, with a 4-component Majorana fermion with the same transformation, then I can write down a time inversal invariant Hamiltonian, okay, which is this one. It's a product of 4 gammas together. There's no I involved, and it's a Hermitian and the time inversal invariant. Okay, but this term can be written like this. It can be written like this. Then now the ground state will be doubly degenerate. The ground state for this Hamiltonian of the 0 dimensions will be doubly degenerate. The reason is that this term corresponds to 2i gamma 1 gamma 2 times 2i gamma 3 gamma 4. This operator behaves just like a Pauli matrix, and this operator behaves like another Pauli matrix and the product. So it means that the ground state of this term will always be twofold degenerate depending on the sign of k. If k is positive, the ground state for this term will be up, up, and down, down. Okay. If k is negative, it corresponds to up, down, and down, up. Okay. And in either case, the ground state will have non-zero average value of this term. It means that the twofold degeneracy of this Hamiltonian corresponds to spontaneous time inverse symmetry breaking. That's the case. Okay, let's go to 8 copy. Okay. For 8 copy, situation becomes a lot more interesting. For 8, I can decompose 8 into 2 groups, gamma 1, 2, 3, 4, and gamma 5, 6, 7, 8. So as I said, the interaction I turned on before will give you a doubly degenerate ground state in this set, and give you another doublet here. But then there are 2 doublets, then I can turn on another term, which also is a 4 Fermi term, but a very complicated 4 Fermi term. I turn on 4 Fermi term to make these 2 doublets become a singlet. Okay. This term will have, it's a very complicated term actually. In terms of Majorana Fermi, it's complicated, but still local 4 Fermi interaction term. It will make a singlet. And this singlet has a gap to all the excited states. Okay. Has a gap to all excited states. And this singlet is non-degenerate. Because the singlet is non-degenerate, implies that the expression value for any formula bilinear operator must be 0. Okay? Because if it's non-zero, it would break time inversal symmetry and give you degeneracy. Okay? And I have a non-degenerate gap state, means that this is always 0. Okay? So this means that the 0 plus 1 dimensional system, it's very easy to show that for 8 copies of Majorana Fermi and 0 mode, we can turn on a 4 Fermi interaction, although it's a sum of many, many terms, turn on a 4 Fermi interaction to gap out the entire system, but once I take the ground state wave function, it has a 0 average value of any Fermi bilinear mass operator. Okay, so this is the mechanism of gapping out a Fermi without generating any Fermi bilinear mass, 0 dimension. It can be solved in that. Okay. And this 0-dimensional boundary is actually, the 0-dimensional system is the boundary of a 1-dimensional system. And this 1-dimensional system looks like this. It's a 1-dimensional Kitaev chain, a 1-dimensional chain, Majorana Fermi chain. It's just a free Fermion hopping, the Majorana hopping from this side to this side, this side to this side. But there are 2 different ways to staggerize the coupling constant. We can make, for example, J2 stronger than J1, or J1 stronger than J2. If I make J2 stronger than J1, then this is a spectrum. Okay, this is spectrum. The ground state is non-degenerate. But if J1 is bigger than J2, then spectrum becomes this. Okay, spectrum becomes this, because every side there will be a unfilled dangling Majorana Fermi 0 mode. Okay. And this 0 mode corresponds to the 0 mode I discussed in previous slide. And I can define a time inversal symmetry in the bulk, which translates to the same time inversal I defined in the previous slide, like this. Okay, so this is the bulk state. Okay, so the analysis I did here, okay, means that for this particular system, if I define time inversal symmetry, then if I do not turn on any interaction, without any interaction, no matter how many copies of this state I stack together, as long as I don't turn on any interaction, its boundary will always be degenerate. However, if I turn on interaction, if I turn on a particular singlet-driven interaction, then for 8 copies of the system, its boundary will become trivial, will become gapped, non-degenerate, and does not condense any Fermion bilinear mass. So it means that this is the first example of an interaction-reduced classification of a topological superconductor. So without interaction is Z, with interaction becomes Z8. Okay, so this is the first example which shows that interaction can change the classification of topological superconductors without any symmetry. Okay. Okay, and you can see that it already gives us some example of the physics I want to achieve in the grand unified field. Okay. So then this kind of physics is also can show up in higher and higher dimensions. Okay. So let me skip 2 plus 1. Let me go to 3 plus 1 dimensional bulk. Okay. So 3 plus 1 dimensional system, there is a famous topological superconductor called helium-3b. So this helium-3b, the bulk is a 3 plus 1 dimensional massive Majorana fermion, and its boundary is a 2. Okay, the bulk is a 3 plus 1 dimensional massive Majorana fermion, its boundary is a 2 plus 1 dimensional massless Majorana fermion. Okay, like this. And time universal will operate this way. Okay. So with this time universal symmetry, you can see that any mass term as the boundary will be forbidden by time universal. For example, if I turn a mass term which is the chi transpose tau y chi, okay, because tau y is imaginary, then it's going to change sign under this time universal transformation. It will change sign. Okay. So and also you can show that as long as I do not turn on any interaction, as long as I only keep at the free fermion level, then no matter how many copies of the system are stacked together, as long as I have time universal defined this way, there's no mass term I can turn on. No mass term can turn on as the boundary. This means that time universal symmetry forbids any fermion bilinear term on the boundary of this system, on this system, no matter how many flavors I give this system. Okay. However, many people actually show that under interaction, the classification for helium 3b is reduced from Z to Z16. This actually implies that with 16 copies of system, with 16 copies of 2 plus 1 dimensional Majorana fermion with time universal symmetry, I can turn on a rather complicated involved 4 fermion local short range interaction, and this interaction can gap out this fermion without breaking time universal symmetry. This means that the fermions are gapped without condensing any fermion bilinear mass. Is that clear? I mean, this statement is clear. Okay, I will show you how they argue that later. Okay, but let me just make sure the statement is understood. Okay, okay. Of course, in a higher dimension, it's going to be very hard to do any exact calculation. So we have to rely on certain argument. Okay, certain argument. So the simplest argument was proposed by Cenke and his student. It goes like this. So let's consider 2 copies of system. Okay, 2 copies of system. Okay, under A equals to 1 and 2. And these 2 copies of the boundary will be 2 flavors of Majorana fermion, and we can couple them to an O2 vector phi x and phi y, coupled this way. And both phi is a mass term. It's a mass term on the boundary. So this means that if I condense phi x or phi y, it's going to break time universal as the boundary. Okay. However, we can try to restore the time universal symmetry. Okay, we can try to restore the time universal symmetry by proliferating the defect of the phi. For example, we can consider how to we can try to restore the time universal symmetry by condensing the vortex of phi. Okay, condense the vortex of phi. Okay, so if I create a vortex of phi by doing the calculation here, you can see that the vortex core will have a localized Majorana fermion 0 mode. It has one localized Majorana fermion 0 mode. And this 0 mode will transform under some modified time universal symmetry the same way as the 0-dimensional fermion I mentioned to you before. Okay, the modified time universal is the original time universal times the pi rotation of phi. Because the under time universal phi will change sign, under pi rotation phi also change sign. So this is a residue time universal symmetry we can define. So the Majorana fermion core state will have to transform non-trivially under this time universal, modified time universal. Now, under the modified time universal symmetry, the gamma will go to itself, and this actually is the same transformation which I mentioned before.
So
okay.
So the t prime square is 1 or minus 1?
It is well, I mean, it's 1. It's 1. Yeah, it is 1. In the modified time universal type t square is 1. Okay. So now this means that. So now if I want to restore the symmetry, restore the time universal symmetry by condensing the vortex, I will have to worry about the spectrum of the vortex. Okay, the goal is to achieve a fully gapped and non-degenerate boundary state. That's the goal. But in order to achieve that, I must guarantee that the vortex core must be gapped and non-degenerate and time universal invariant. Okay, that's what I must guarantee. Okay, so previously I showed you that without interaction, it cannot be achieved at all. Without interaction, no matter how many copies of 0 mode here, it will always be degenerate. However, with 8 copies of this from 0 mode, there is an interaction which can gap it out without generating any fermion bilinear mass, without breaking any time universal symmetry. Okay, Okay. This means that when and only when I have 8 copies of this system, which becomes 16 copies of the original helium-3b, I can condense the vortex to restore all the symmetry while keeping the system gapped and non-generate. Okay. That's their argument. That's their argument. So that's why we reduce Z to Z16. Okay. So let me also show.
Before you go on, so in the previous slide, it's similar to the Higgs mechanism.
Higgs mechanism.
But the Higgs mechanism sort of gives a mass to both left and right fermions. But in the previous slide, you sort of just get out just the right.
No, it's 2 plus 1 dimensional fermion. There's no right or left hand, right? I'm talking about 2 plus 1 dimensional fermion. There's no hand. There's no karatic in 2 plus 1.
But in this construction, did you get out just part of the fermions?
Well, all fermions, right? So the strategy is that phi, I mean, when I condense phi, fermions already gapped. So I can ignore the background fermion now, right? Low energy. Then I just create a vortex. And I want to worry, so I have to worry about whether the vortex has a gapless or gap spectrum, right? Because I want to condense the vortex to restore all the symmetry. If the vortex is the 5x, 5y vortex, right? If I order an O2 vector and I disorder it, how do I disorder it? I just condense the vortex to disorder it, okay? But if I condense the vortex, the only way I get to a fully gapped non-generate state is when the vortex core is fully gapped non-generate. Otherwise, I will get degenerate state. I can show you why that's the case, okay? So in 2 plus 1 dimension, we have a very well-known duality formalism for condensing vortex. Okay. So in the dual formalism of a superfluid, the vortex becomes a local field, and there's a U1 gauge field A. The U1 gauge field A corresponds to is a dual mode of the Goldstone mode, the dual Goldstone mode. Okay. So this is a theory for condensing the vortex. So suppose the vortex core is degenerate. Okay. Suppose the vortex core is degenerate. It means that the vortex have different species. There's a different, different state of the vortex. It could be 1 to n. Then this is the CPn minus 1 model. Okay. And we know that this model, when V condense, it will give you degenerate ground state. However, if the vortex has no degeneracy at all, it means that the vortex has only one component. Then the condensate vortex actually will be a fully gapped, non-degenerate state. Okay, that state we are after. It means that the system only become a fully gapped non-degenerate state after I condense the vortex, when and only when I have 16 copies of the helium-3b. It means that only in that case I can have a vortex core which is fully gapped non-generated by interaction. Okay. That's the simplest argument for why the classification is reduced from Z to Z16. Okay, so in higher dimension, unfortunately, we cannot solve things as precisely as 0 plus 1 dimension, so we will have to use arguments like this. Okay, so let me remind you our ultimate goal. Ultimate goal is that we want to construct a 4-dimensional state whose boundary is a standard model or one of the grand unified theory, and we want to argue that without interaction is non-trivial, and with interaction becomes trivial. So it means that with a weak interaction, I can guarantee the top surface is a grand unified theory, but with strong interaction, the bottom surface will be gapped without condensing any further magnetic mass. Okay. So I found one particular grand unified theory, most easy to do this argument. It's the Patti-Salam grand unified theory. The Patti-Salam grand unified theory still has 16 left-handed chiral fermions, and its representation, the group will decompose into the SU4 cross SU2 cross SU2, 2 SU2s. And they form representation 4, 2, 1, and 4 bar, 1, 2. Do I need to explain the notation? Okay. For example, the 16 will decompose into 8 and 8. The first 8 fermion will form an SU4 fundamental on the SU4, and SU2 fundamental on the second SU2, but singlet under this SU2. But next 8 will form a 4 bar on the SU4 and singlet on the SU2, but doublet on the second SU2. Okay. That's how you get this 4 times 2 plus 4 times 2 equals to 16. Okay. So our goal is to show that the 4 plus 1D topological insulator with SU4 cross SU2 cross SU2 symmetry is non-trivial without interaction, but trivial under interaction. Okay, that's the goal. Okay, so how do we argue a topological insulator is trivialized by interaction? There are 2 ways to argue that. Okay? In the case of helium-3b, the way we argue the 16-copy helium-3b to trivialize by interaction is by directly arguing that the boundary is gapped out without interaction by, it's gapped out without symmetry breaking by interaction. That's a direct way of arguing the boundary. Another way to make the same statement is to say that the topological insulator to trivial state phase transition in the bulk is gapped out by interaction. Okay? That's another way to argue that. Question? No, it should be superconductor. It should be, there's no extra U1. Yeah, no extra U1. And U1 is anomalous, so it must be gone. Yeah. Right, so the second strategy to argue something trivialized interaction is by saying that it's a bulk quantum critical point between trivial and a topological state is gapped out by interaction. It means that interaction can give you a adiabatic path from topological trivial state, okay, without going through any phase. So these statements are equivalent. So here we will take the second strategy. Okay, take a second strategy. Okay, so this is the bulk phase diagram. It's a bulk phase diagram. So this is the bulk Hamiltonian. Okay, it's already a field theory Hamiltonian, but we can write down lattice Hamiltonian with no problem. Okay, so the field theory Hamiltonian with 1 tuning parameter m. When m is greater than 0, this state is a topological superconductor, actually. When m is smaller than 0, this state is trivial. So without interaction, there has to be a phase transition in the bulk where the system gap closes at m equals 0. Okay, there must be a phase transition. So our goal is to argue that interaction can give us an adiabatic path from this side to this side without going through any phase transition. Okay, that's the goal. So how do we argue that happens? So let's try to follow Centel's argument in the previous case. Let's try to break part of the symmetry by condensing some fermion bilinear order parameter. And then let's try to proliferate or condense the defect of those topological, condense the defect of those order parameter. And all we need to argue is that the defect core, okay, is trivial. That's all we need to argue. Okay, that's all we need to argue. So turns out that here, the simplest defect we can condense is the O4 vector. The reason is that this symmetry contains SU4 cross SU2 cross SU2, and SU2 cross SU2 is an O4 vector. Okay, so we can construct a 4-component unit vector or the parameter O4 vector, and it's going to couple to the fermion and gap out the fermion in the bulk, and break the SU2 symmetry. Global. So far, no gauge field yet. I know. So all the physics here I'm discussing is global symmetry. But if the global symmetry works, there's no trouble to gauge it. Okay, there's no problem to gauge it. We can just add some links to the system, and I think there's no problem gauging.
But in the standard model, actually this denomination is from the kind of abelian quantity.
I know U1 will be broken. U1 will be broken by my interaction. There will not be any anomalous U1.
Yeah, but if no U1 is just SU2, there's no ABJ anomaly, then you have this discrete and SU4 is also
No, this model has no anomaly at all. This SU4 has a 4 and a 4 bar. And this SU2, these two SU2 both have doublet. Both have 2 copies of doublet, so there's no anomaly at all in this model. There's no known anomaly at least. Right? So no chiral anomaly, no Wheaton anomaly, no any known anomaly.
I think here we try to show there's no unknown anomaly as well.
Yeah, I'm trying to show there's no known anomaly as well. Yeah, there's no known anomaly. There's no unknown anomaly. There's no unknown anomaly. Sorry? Chiral fermion, yes. Yes, that's what I'm gonna do. But I will explain why that is the case. Okay, why that is possible, and why that bypass those no-go theorem. No-go theorem assumes something very, very strong. Okay, which I.
But if there's no U1 symmetry in the sense it's chiral fermion, because the chiral fermion should be defined as immediate anomaly or
No, chiral. No. I mean, yeah. Let's change the definition of chiral fermion. Okay. In the Presque mechanism, they also do the same thing. Okay, if you want to realize standard model, any lattice model without a mirror section, the U1 symmetry must be broken because the U1 symmetry is anomalous. That symmetry must be broken, and that U1 symmetry is assumed in the no-go theorem.
I'm just asking what's the definition of chiral anomaly without.
There's no chiral anomaly. I'm saying there's no chiral anomaly at all. If you have anomaly, it cannot be.
In this sense, there's no chiral fermion.
Why is that? It's all the low energy experiments is precisely the same as standard model.
Yeah, so my question is what's the definition of chiral fermion without this type U1?
It's described by one Hamiltonian. It's just a side dagger I sigma y partial psi is Hamiltonian. That's my definition of chiral fermion.
But there, if you use this y representation, there's always U1 symmetry.
Yeah, but U1 is emergent. That's the key. I mean, you came in late, okay? So previously I gave a few slides to explain this, right? We have to break the U1 symmetry on the lattice, but the U1 symmetry can emerge at low energy. That's the whole key here. So at a low energy, this system behaves like chiral fermion. There's no low energy experiment you can do to distinguish this from the true chiral fermion. But
if U1 is emergent, the velocity of all these fermion goes on the U1 field and not necessarily the same.
in condensed matter, we never worry about that.
Yeah, but in our fundamental work, it's the same. So.
Well, does anyone have a solution for that actually?
So there are a few things. First thing, given this area of power fermion, I mean, yeah, the energy experiment and the anomaly here, but they are anomaly canceling. If the number of the power fermion is correct,
Yeah, let me go back to since a few people came in late. Okay, they missed the important part of my talk. So let me go back. Okay. Okay, this is their famous paper. Okay. So the explicit assumption they make is this: okay? Exact conservation of charge. And this even at scale when the lattice cutoff is relevant. It means that they have to assume an exact U1 symmetry on the lattice. If we assume an exact U1 symmetry on the lattice, then a single chiral fermion cannot exist in 3+1 dimension. Okay. However, I said there's a room to cheat. Okay. Which means that we can break the U1 symmetry on the lattice scale, but make this U1 symmetry breaking term irrelevant at the low energy. It means that if I go to UV, I'm going to see the U1 symmetry breaking, but at low energy I will not. So it violates that condition. It violates this condition. Violates this assumption. However, because at the low energy, this U1 symmetry is exact and it emerges at low energy. There's no low energy experiment you can do to distinguish this from a chiral fermion that you want to get. However, this U1 symmetry, because it emerges at low energy, it cannot be gauged. So there's no anomaly here. It can never be gauged. Okay? It can never be gauged. So this is in condensed matter, we have an emergent symmetry all the time.
Okay. Trying to say, for example, so usually in field theory there's a surface anomaly type condition for
Yeah.
U1 which persists at UV.
Yeah, the U1 cannot be gauged.
Say basically at UV because there's no such a U1.
Exactly.
There's no surface anomaly.
Exactly, yeah.
In IR, even though there's such a but the global symmetry is different in this case slightly.
No, I don't think that this is so different at all. So here, let's remove all the gauge fields, right? If there's an exact global symmetry, if the exact global symmetry at on the lattice, then I can gauge it with no problem. Okay, and if I see gauge anomaly this way, it means that this symmetry is problematic. Okay, symmetry problem. We assume something too strong. Okay, this symmetry cannot be there. Okay, this symmetry cannot be there. This symmetry has to be broken on the lattice scale. but that symmetry breaking term may be irrelevant.